We're going to derive an equation for the kinetic energy of this hollow sphere in terms of mass, radius, and velocity, and other fundamental constants. So the kinetic energy of this object, it's going to be rotating. It's so first of all, it's rolling without slipping, and it's also translating. So it has rotational kinetic energy and it has translational kinetic energy. But I think for now I'll put the translational first and then the rotational kinetic energy here. Now we know very well what the translational kinetic energy is. This is mv squared over 2. And the rotational kinetic energy is I omega squared over 2. And just looking here, we need it in terms of mass, radius, and v. We have mass v here. And so this expression over here, we need to change this, substitute it for some expression in terms of mass and velocity. And so we will do that. Mv squared over 2 plus. Now, the rotational inertia of a hollow sphere is 2/3 mr squared. And we don't want to do this where we have stacked fractions, and then we have omega squared over here. So here's what we're going to do instead. We're going to write these as three separate fractions. So the 2 down here, well, that's like a 1 over 2. That's 1/2, which we're going to bring out to the side. Now we'll put in the rotational inertia of a hollow sphere. This is 2/3 mr squared. Let me zoom in here. And omega, we can't leave it as omega squared, but in our notes, we have this relationship that v is equal to r omega. And so if we rearrange this for omega, this is v over r, but it's squared. So v over r and this whole thing is squared. Well, v over r squared is v over r times v over r, which is v squared over r squared. So I'll put this here as a little intermediate step. So 1/2, 2/3 mr squared over 3. And we can cancel out a few things. We can cancel out 2, we can cancel out r squared, and so we're left with mv squared over 2 plus, okay, the 1 kind of drifts off there, this is v squared over 3. And we can combine these, mv squared, you can combine these, just get a common denominator, which is 6. And so this would be 3 mv squared over 6 plus 2 mv squared over 6, which of course is 5 mv squared over 6. And that is our equation for the kinetic energy of a hollow sphere. Okay. So another hollow sphere. This time we know the mass, we know the radius. It's on a slope which is angled at 30 degrees. And the hollow sphere is at a height of 6 meters. We want to know what is the kinetic energy of this hollow sphere at the bottom. And by the way, this is starting from rest. Oops, that didn't come out the way I wanted. It's a hollow sphere. Okay. And we want to know what is the translational speed v at the bottom. Okay, and then we'll keep going there in just a moment. Now, you could solve this you can solve this two ways. You can also solve this using kinematics and our equations for acceleration and angular acceleration. Um, but we're going to solve this using energy concepts. And so for part A, let's figure out K. Energy at position 1 is equal to energy at position 2. And so we'll do this. There's no springs here. And what they're asking us for question A is what is the kinetic energy at the bottom? This would be position 2 down here. We're just trying to find out K2. That's it. K2 equals something. And it's starting from rest, so there's no kinetic energy at position 1. This would be height 1. It does have gravitational potential energy, but at the bottom of this ramp, there is no gravitational potential energy. This is mgh1 equals K2. So this is 4 times 10 times 6 is K2. That's 240 joules is K2. And then V, we will figure out what is V at the bottom. Well, don't we know K2 in terms of, it's 5, 6 mv squared, so we know it in terms of V. But, assuming we didn't know that, let's say it's some other object, maybe a solid sphere, we would have to do something like this, which we just did. A rotational. But as it turns out, we've done this already. This is m v squared over 2 plus um, I omega squared over 2. And yeah, I'm just going through the motions of solving this again. We would put in the rotational inertia of that object. In this case, it's still the hollow sphere, so that's 2/3 mr squared. But if it was a solid sphere, you get 2/5. Or if it was a disk, you would get, you get the idea. This is V over R. I'm just going to say it's V squared R squared because it's omega is V over R, but you square this and then you square this one. And we just went through this. This is mv squared over 2 plus mv squared over 3, which is 5/6 mv squared. And let's solve for v. So I'm going to rearrange this. This is 6 times K2 over 5 times the mass is v squared. That is 6 times 240 over 5 times 4 is v squared, which is 72. We take a square root. And so this is, oh, so I forgot what this is. Let's type this in here real quick. Sorry about that phone. This is 8.49. Okay, let's do part C real quick. Yeah, what is the translational kinetic energy at the bottom? Well, we do have an expression for that, which is simply this. So you can just right, mv squared over 2, and we will plug that in. This is 4 times 8.49 squared over 2. And that comes out to, oops, 144 joules. We can do the same thing for rotational kinetic energy, which is, sorry, part D. Now, you could do this if you want to torture yourself. Just do this one. And in fact, there's an even easier way. So 4, 8.49 squared over 3. That looks messy. Except that this is a 3. And of course, we get 96 joules. So the even easier way to do this is, K2, we know it's 240. KTR is 144. And you subtract those, this would give you 96. Oops. Of course, you would want to show proper work. I was just trying to make the video short. You could show this equation here, and you can plug in 240 for that. You can plug in 144 for that. Take your steps, take your time. Now, if you look at this, and you look at this conservation of mechanical energy, you might remember that we said that this is true only if there are no non-conservative forces doing work. No non-conservative forces, conservative forces doing work. And the obvious non-conservative force we're speaking of here is friction. Isn't there friction on this thing? If we draw a free body diagram, there's friction right here. And is that friction doing work? Well, yeah, long story short, it's doing work. So it's doing work. But it turns out it's doing both negative work and positive work. It's doing negative work translationally here, because friction is pointed off in this direction. And the distance, if you remember our equation, work is equal to force times distance. And our distance would be some distance here. And those are in opposite directions. So that's negative work, and I should show that. But it's also doing positive work because it's contributing to that rotational kinetic energy of the hollow sphere. So as it turns out, it does equal amounts of positive and negative work. And so this term is still 0. And so everything is all right. What we did here is fine. Cool. And that's it for this lesson here.